The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
First, I'll thank you to giving me the chance to speak today. In my presentation today, I will address the development length of high-strength bars in tension. First, I'm going to give you a background, then I'm going to talk about the ACI 408 equation. I'm going to show you also some high-strength reinforcement data and the proposed simplified equation. And finally, I will show you some comparisons and concluding remarks. 408, ACI 408 document for bond and development of straight reinforcing bar in tension proposed a design equation for straight bar development. This design equation was based on 320 test specimens with and without transverse reinforcement. These test specimens included bar sizes from number 4, number 14, with concrete compressive strength range from 1800 to 16,000 psi, and bar stresses at failure ranging from about 28 to 118 KSI. The ACI 408 database consisted of mainly beam end specimens, beam anchor specimens, consists of beam end specimens, beam anchor specimens, splice specimen. The bulk part of ACI 408 database were splice specimens. This figure is showing a typical splice specimen that was tested. Think about splice specimens that they are easy to construct and test, and they've been used widely, universally by many researchers. Among those researchers, we have Ferguson at the 50s, Yerson in the 70s, Darwin in the 90s, and Salim, most recently Salim in 2007. So, we are talking development length, so the question is why we are using splice specimens to predict development length. Now, this will take us back to a study from Orangan, Yerson, and Breen in the 70s, where they stated that a similar behavior in cracking and splitting has been observed in tests for development length and lab splices. And they concluded that the development and splice lengths were found to be identical. So that's telling us that splice tests can be used directly for calculating development lengths. Noting that ACI 318 equation was based on the recommendations from Orangan, Yerson, and Breen. So this slide shows the 408 equation. We see that the development length is a function of bar yield stress, concrete compressive strength to core power, and a confinement term. That confinement term has a limit of 4. What's really we want to note about this equation that F prime C to the core power is in contrast with what we have in ACI 318, which is a square root. Also, something else to note that the development length is not linearly proportional to the yield strength of the bar. That's telling us that if we double the yield strength, we will need to have more than double the development length that we need. Usually in order to get the accuracy of the equation, we deal with the test over calculated ratios. What we do is we solve the equation for stresses, and then we calculate them and compare them with the measured stresses. For this equation, when using a phi factor of 1, the test over calculated, if it's greater than or equal to 1, that means the specimen is safe. So the equation gave us a mean of 1 with coefficient of variation of 11% for specimens without confining reinforcement. For specimens with confining reinforcement, it gave us a mean of 1.04 with coefficient of variation of 14%. The confinement term consists of effect of the cover, spacing, area of transverse reinforcement, and diameter of the bar. The spacing is a function of maximum spacing, minimum spacing. The KTR reinforcement index is a function of TR, which is a function of relative rib area. TD is a function of diameter of the bar, area of transverse reinforcement, spacing between stirrups, number of hook bars, number of bars being developed, and concrete compressive strength. That's telling us that calculations are involved in this equation, and for practice, this equation needs to be simplified. Getting the test over calculated stress ratio for a 408 equation after incorporating a reliability-based factor, phi factor, the mean goes up to 1.23, coefficient of variation stays the same, and percent of specimens with test over calculated less than 1 were 6% for specimens without confining reinforcement. For specimens with confining reinforcement, the mean of test over calculated was 1.28, coefficient of variation stays the same, and percent of specimens with test over calculated less than 1 was 4%. Now, the most recent study for high-strength reinforcement data was reported by Salim et al. In 2007. He reported 69 splice tests with high-strength reinforcement. What they did is they compared the test data that they have with the current ACI 318 equation and 408 equation. So this figure shows the test over calculated stress ratio in y-axis and bar stress in the x-axis. The blue dots showing ACI 318 and the red dots are showing the ACI 408, or the ratios calculated using that equation. For specimens without transverse reinforcement, they found that 65% of specimens had test over calculated stress ratio less than 1 using 318 equation, while only 5% of the specimen had test over calculated less than 1 using 408 equation. For specimens with confining reinforcement, they found that 30% of the specimen had test over calculated less than 1 using the current 318 equation, and none of the specimen had test over calculated less than 1 using ACI 408 equation. Salim et al., Salim concluded that ACI 318 equation should not be used for development and splice design with high strength reinforcing steel in their present form. That's telling us that we need a new equation. Now, the main goal was, after many attempts, was to simplify the current ACI 408 equation, incorporating ACI 318 variables. The equation that we got is similar. We have a psi-y term that accounts for the nonlinearity here, which has this form. As a function, yield strength factor. Also, we introduce an omega, which is spacing factor. The spacing factor is applied when we have widely spaced bars. Usually, widely spaced bars are stronger than closely spaced bars. So when we have a clear spacing between the bars, greater than and equal 6 times the bar diameter, omega will equal to 1.25. This will add an economy for most slabs and walls and footings, because it's going to decrease the development length required. Now, the final design expression, after incorporating the modification factors for casting position, coating factor, lightweight concrete factor, will have this form. Now, after showing you the final design expression, now we are comparing the data that we have so far. So, using the expanded database, which include 408 database, in addition to the 69 specimens reported by Salim et al., the plot to your left is showing ACI equation, comparison with ACI equation, and to the right is showing the proposed equation. And the vertical axis represents test over calculated stress ratio. The horizontal axis, or the x-axis, represents concrete compressive strength. Again, if we have test over calculated less than 1, that means it's unsafe. So for 318, we found that 29% of the specimen had test over calculated less than 1. With the proposed equation, we had only 7% of the data with test over calculated less than 1. And this is for specimens without transverse reinforcement. Now, For specimens without transverse reinforcement, but they have stresses greater than 80 KSI, we found that 59% of the specimen using the current ACI equation had test over calculated less than 1, while none of the specimens using the proposed equation had a test over calculated less than 1. Now, using the whole database with specimen with transverse reinforcement, same comparisons made, we saw that 22% of the specimens using the current ACI 318 equation had test over calculated less than 1, while 4% of the specimens had test over calculated less than 1 using the proposed equation. When using the specimens with confining reinforcement, with the stresses greater than 80 KSI, same comparison was made, and we found that 39% of the specimens using the current ACI provision, 318 provision, had test over calculated less than 1, and none of the specimens had test over calculated less than 1 using the proposed equation. Now, another comparison was made by assuming grade 100 steel with the minimum confinement provided by the confinement term and keeping all the modification factors as 1. What we did is we plot the development length. We calculated and plot development length normalized by diameter of the bar in the y-axis versus concrete compressive strength in x-axis. The blue line represent ACI 318 and the red line represent the proposed equation. We see that ACI 318 predicts shorter development length from 30 to 60% and get worse. They are providing minimum than what's required, and it's getting worse with increasing the concrete compressive strength. And that's because of the using of the square root for F prime C. Same comparison was made, grade 100 steel with fully confinement, making use of the confinement term for the current equation going up to 4, and it's limited for ACI 318 equation to 2.5. Same comparison was made, ACI in blue and proposed equation in red. It's showing that even though they are close together, predicting closer development length, but that means that ACI only predict realistic development lengths when it's fully confined. That's telling us that the margin of safety that ACI 318 is providing is not uniform along the whole confinement or along the whole data. Also, for lower strength concretes, ACI, the calculated development length using ACI is about 20% longer than what's required. So, summarizing to my presentation, I want to reiterate what I said. It's that the ACI 318 development length equation for stresses greater than 80 KSI, the calculated, test over calculated was less than 1 for 59% of the specimens without transverse reinforcement, and it was less than 1 for 39 specimens with transverse reinforcement. And the proposed development length equation has 0% of specimens with test over calculated less than 1. Also, one important factor is that the proposed equation promotes the use of transverse reinforcement to reduce the development length for high strength and conventional strength reinforcement. Thank you.
We have time for a couple questions.
Yes, sir.
I think what we found with the influence of the specified yield strength that agrees what we found. We had a different equation for that, but the increase is about 50% in your case, 30 and 60%. I think that agrees quite nicely. I didn't show the graph where we investigated the influence of the confinement. I agree with you as well that the ACI limit from 2.5 can increase to 3.5 or 4. Where I do not agree with you, the equation currently you propose gives again the 5% factor of your more or less of your results is equal to the specified yield strength, which I believe is not sufficient to really prevent slice failure. But otherwise, I agree with you.
Well, thank you for that. The thing is about the specimen database, I mean, they are showing that good agreement with the test results. So, and also beside that, the plots that you're showing also had some failures, right? Below 1. So it's kind of similar trend, I guess.
Thank you.
Thank you.